Hi, my name is Amy, and this is my Lab 3 video report on circuits. I used the circuit kit simulation to study current, voltage, resistors, and capacitors. The purpose of this lab was to study DC and RC circuits by measuring current and voltage with ammeters and voltmeters. I tested the loop rule, node rule, Ohm's law, and capacitor behavior. The system was the circuit and the surroundings were everything outside the circuit. The main physics principles were current conservation, energy conservation, Ohm's law, capacitance, and RC behavior. The node rule says current entering a point equals current leaving. The loop rule says the total voltage change around a closed loop equals 0. Ohm's law is delta V equals current times resistance, and capacitance is Q equals C delta V. For the first part, I built a series circuit with two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters. The total battery voltage was 3 volts, and the total resistance was 147 ohms. Since it was a series circuit, there was only one path for current. To predict the current, I used Ohm's law. Current equals voltage divided by resistance. So 3 volts divided by 147 ohms gives 0.0204 amps. Both ammeters should read about 0.02 amps because current is the same everywhere inside a series circuit. The measured current was about 0.02 amps, and both ammeters showed the same reading. This matched the prediction and supported current conservation because charge was not building up anywhere in the circuit. Next, I measured the voltage across the resistors. The 100 ohm resistor had a voltage of about 2.04 volts, and the 47 ohm resistor had a voltage of about 0.96 volts. The 100 ohm resistor had the larger voltage drop because it had the larger resistance, and the same current flowed through both resistors. The batteries gave the circuit about positive 3 volts. The resistor had voltage drops of about 2.04 volts and 0.96 volts. So positive 3 minus 2.04 minus 0.96 equals 0 volts. This means the round-trip voltage change was about 0, which supports the loop rule and energy conservation. Across the wire or ammeter section, the voltmeter read 0 volts. This makes sense because ideal wires and ideal ammeters have almost no resistance, so they have almost no voltage drop. When the voltmeter replaced part of the circuit, the current became about 0 amps because a voltmeter has very high resistance. For the RC part, I used a battery, a bulb or resistor, and a capacitor in series. When the capacitor charged, the bulb started bright and then dimmed as the current decreased. When the capacitor discharged, the bulb lit briefly and then faded as the capacitor lost charge. The capacitor voltage changes exponentially. Delta V equals delta V initial times e to the negative T over RC. RC is the time constant. A larger resistance means a longer charge and discharge time, so the 20 ohm bulb took longer than the 10 ohm bulb. Possible sources of error included rounded meter readings, probe placement, and timing the capacitor charging and discharging. The model also assumes ideal wires and meters, but real wires, meters, and batteries have some resistance. If a real ammeter was used instead of an ideal one, it would have a small resistance, so it would slightly lower the current. If a real battery charged a capacitor with no resistor, the ideal model would predict instant charging. In real life, it would not be instant because batteries and wires still have internal resistance. Overall, the series circuit behaved as expected. The current stayed constant and matched the predicted value of about 0.02 amps. The voltage drops added to the battery voltage, so the loop rule worked. The RC circuit showed that capacitors charge and discharge over time, and higher resistance increased the time.